Khan, and today I'm excited to present RL Pruner reinforcement learning meets network compression. And in this presentation, I'll explain how RL Pruner leverages reinforcement learning to make convolutional neural networks smaller, faster, and more efficient for real world applications. So we'll go on to the next slide for this. So, artificial intelligence itself has revolutionized industries like healthcare and autonomous driving. At the core of many AI systems are convolutional neural networks or CNNs, which are incredibly powerful at processing visual data. However, CNNs come with significant challenges. So, they are often bulky, computationally expensive, and difficult to deploy on resource limited edge devices. For example, I even worked on a trash classification project that was using CNNs. So while the model performed well in a controlled environment, I think deploying it on a smaller devices proved challenging due to its large size and high computational demands. So this highlights the need for lightweight solutions. We'll go on to the next slide. So what's the problem we are trying to solve? Traditional CNNs are large and resource intensive, making them unsuitable for edge devices like IoT or smartphones. So this leads to unstable, inefficient performance, which especially in real-time applications. To address these challenges, we need a solution that reduces the size and computational costs of CNNs without making less change in the accuracy or efficiency of it. And we'll go on to the solution slide. So the solution that we are going to present is RL Pruner, a revolutionary technique that uses reinforcement learning to prune unnecessary parts of CNNs. So let's look at it like this. Instead of manually deciding which parts to prune, RL Pruner dynamically learns the optimal pruning strategies, and it makes CNN smaller and faster while retraining high accuracy, enabling real world applications or on edge devices. Real world applications or real time applications on edge devices. We'll go on to the next slide. So how RL Pruner works? So briefly, as you can see, it's a four-step process, and there's a dependency graph, and then the layer-wise sparsity, and then layer pruning, and then knowledge distillation. So we'll take a closer look into all these four processes, and we'll start with the dependency graph. So RL Pruner begins by analyzing the CNN architecture to understand the relationships between layers. A dependency graph is created to map out how pruning one layer impacts others. This is basically creating a relationship between different layers, and then determining how one layer is going to impact the other. And then there's layer wise sparsity. So RL Pruner, what it does is it assigns pruning levels dynamically using reinforcement learning, determining which layers to prune more and which layers to prune less. Further, we go on to layer pruning. So filters are pruned based on their importance. So first we decide from layer wise sparsity which one is more important, and we do it accordingly. We prune it accordingly. So for this we use a Taylor criterion. This ensures minimal impact on model performance. And then there's the last step, which is knowledge distillation. So finally, RL Pruner uses the original model as a teacher to fine tune the pruned model, recovering any lost performance. So the original model we had, the bulky model, we're going to use it further as a teacher or as a guide to fine tune this pruned model. Next slide is a working diagram which I'm going to briefly explain. So the first step, as you can see, it's initializing the prune distribution. So here what happens is we start with a pre-trained model consisting of convolution, batch normalization, and linear layers. The initial pruning distribution is defined where each layer is assigned a level of prune sparsity. This step sets like a baseline for the overall pruning process. And then for the second step, we have generating new distribution and prune model. So here what happens is Gaussian noise is basically added to the current pruning distribution to create multiple variations. These variations represent different pruning strategies applied to the model. So after pruning is done, the sparsity distribution for each layer is updated based on the replay buffer, which stores information about previous pruning actions and rewards. So it keeps on updating every time um, based on the replay buffer. So it keeps on updating every time based on the replay buffer. And the replay buffer, what it does is it stores information about previous pruning actions and rewards. And then further, the last step or the of the working diagram represents evaluating the compressed model. So the compressed model is basically evaluated on two key metrics. They are test error, and then the other one is compression ratio. So test error ensures minimal accuracy loss, and then compression ratio measures the effectiveness of pruning. How much is compressed is basically the compression ratio, and then each strategy is assigned a reward. So each strategy is assigned a reward. These two key metrics are assigned a reward, and these rewards are stored in the replay buffer to guide further pruning decisions. So this test error and compression ratio of each like pruning process is saved as a reward in the replay buffer. This entire process you see here, it's mostly iterative. So what happens is RL pruner keeps on refining its pruning strategy dynamically until an optimal configuration is achieved. And we'll go on to the next slide. So the results that matter from the study that I got were RL Pruner demonstrated impressive performance. So for the VGG19 model, it achieved like 60% channel sparsity with less than 1% accuracy loss. And then for MobileNet V3 large, it achieved 40% sparsity with minimal performance drop. It was almost similar to VGG19. And then when compared to other methods like DebGraph and GNN RL Pruner consistently like outperform them in terms of accuracy, retention, and then compression ratio. So it was a pretty ideal choice for CNN compression. And these results basically show that RL Pruner effectively eliminates redundancies in CNNs while maintaining predictive power. Since there is not a lot of accuracy loss, I think compressing these models to make it reach the edge devices is a very big plus. And we'll go on to the next slide to see its real world applications. And so how can RL Pruner make a real world impact? So as you can see, we have listed out 3 points. I'll start on with the first one. So faster image recognition. So RL Pruner, what it does is it enables real-time processing for devices like drones and cameras, and thus it reduces the need for cloud-based processing. If it does it on its own, then you don't need a cloud environment or a cloud storage to run these functions. And then for wearable devices, it supports efficient health monitoring and environmental sensing in devices like smartwatches. And then autonomous vehicles. So RL Pruner reduces latency, enabling faster and safer decision making for self-driving cars. And these applications highlight how RL Pruner bridges a gap between modern AI and practical use cases. And we'll go on to the next slide. The last slide is for conclusion, and I believe to wrap this up, I would say RL Pruner is a revolutionary step forward in making AI more efficient and accessible. So by combining reinforcement learning and structured pruning, it achieves very high compression while retaining the performance. So this approach, what it does is it basically paves the way for deploying powerful AI models on resource constrained devices. So let's say, for example, from variables to autonomous vehicles, the the need for this kind of technology is very high. And I believe the future of lightweight AI is very exciting, and RL Pruner is leading the charge for this. And It was really interesting learning about this technique, and I hope I get to apply it sometime in the future. That's about it for this presentation. Thank you so much.